We're going to talk about characteristics of our polynomial functions. So the first few vocabulary words we want to talk about. The first one is extrema. The extrema represent all of the maximum or minimum points of a graph. Now in our graphs, we can have absolute maximums and absolute, or we can have relative max and mins. An absolute maximum is the lowest point on the graph. Now, some graphs do not have a absolute maximum. I'm sorry, the maximum is the highest point on the graph. The minimum, absolute minimum, would be the lowest point on the graph. Now, if you ever hear us talk about a relative maximum or a relative minimum, the relative maximum is just the highest point in a section. Highest point in a section of the graph. And I'll show you what that looks like in our graphs here in a second. The relative minimum is the lowest point of a section of a graph. So we'll take a look at some of our polynomial graphs. So this one starts with fourth degree polynomials. So notice it's x to the fourth. Looks kind of like that. The number of extrema. This one has one minimum. It's the lowest point of the graph. It's an absolute minimum. Notice this graph, it's still an x to the fourth graph, but it has 3 extrema. Notice it has 2 of those represent a maximum, and this one in the middle represents a relative, these 2 represent minimums. This one represents a relative maximum. It's not the highest point of the whole graph, it's just the highest point in this section of the graph. Okay, let's look at our fifth degree polynomials. So here's an example of x to the fifth. And we want to know how many extrema do we have? How many maximums or minimums? Well, I don't have any. It just starts at the bottom and it keeps going all the way to the top. Now this is still an x to the fifth, but if we add something to it, how many extrema do we have now? Well, I have this one and this one. A relative maximum and a relative minimum. I have 2. We're still an x to the fifth graph, but we've added some more things. And let's count. I have 1, 2, 3, 4. Notice I had relative maximums and relative minimums. Let's continue. A sixth degree polynomial. Well, that looks kind of like my quadratic graph or my fourth power graph. It has 1. This one, 1, 2, 3. And now we have to count carefully here. 1, 2, 3, 4, 5. It's a little tiny hump in there. So notice something interesting about these numbers. This was a fourth degree. Look at my possibilities. 3 or 1. My fifth degree, look at the possibilities. 4, 2, or 0. My sixth degree, 5, 3, and 1. Do you notice that all of those, the highest number of extrema they could have is 1 lower than the degree? And then it goes by 2. A sixth degree polynomial cannot have 4 extrema. It has to have 5, 3, or 1. But your extrema always start 1 lower than the degree of your polynomial. So on the next page, we're going to choose always, sometimes, or never. An odd degree function will have an absolute extrema. Well, remember our odd degree functions have a domain of all real numbers? So this is never odd degree functions can never have absolute extrema. How about an even degree function? Can they have absolute extrema? Always. Think about your fourth power and your sixth power that we just demonstrated on the previous page. An even degree function will have 3 or more relative extrema. Well, I think that's a sometimes, because we just demonstrated we could have 1, we could have 3, we could have 5. It just depends. An even degree function will have relative extrema. Not always, but sometimes. Because my graph could look like this, and that has a maximum extrema, but doesn't have a relative one. An odd degree function will have relative extrema. I'm going to go back and amend what I just said. An even degree function always has relative extrema, because we're going to say that all of the extrema are relative and some of them are absolute. So we're going to all extrema are relative. Some of them are absolute. An odd degree function will have relative extrema. Sometimes. Remember, sometimes they didn't have any, and sometimes they had 2 or 4. An odd degree function will have 1 relative extrema. If you looked at our examples on the previous page, we were always 1 number lower than the degree. So if it's an odd degree, it can't have 1. It has to have an even number. So this would be never. An odd degree function will start one number below its power. So let's look at some graphs. Consider these 2 graphs. We're going to answer these 8 questions about each of these graphs. So here we go. For my first graph, is the a value positive or negative? Well, notice it's a down and then an up. Well, that's an odd function, odd degree function, and that's a positive a value. Next question, is the degree even or odd? Well, since they're going opposite ways, that's odd. Can this function be a 6th degree polynomial function? Well, no, because we just said it was an odd degree. State the domain. Well, for my odd functions, the domain is all real numbers, and we could have just said R. State the range. Same thing. For my odd functions, it's all real numbers. Determine the number of relative extrema in this graph. Well, let's count them. 1, 2, 3, 4. Determine the number of absolute extrema. Well, none of them were absolute because an odd function does not have absolute extrema. State the intervals where the graph is decreasing. Alrighty, so if I trace it from left to right, from here to here, grab a highlighter. It is decreasing here, and it's decreasing here. So let's express those intervals. Let's say, was it negative 2.5 to 1? And then over here from maybe 1.5 to a little more than 2. So I'm just guessing here to 2.2. Now, because this had 4 relative extrema, it could have been an x to the 5th graph or anything larger. It couldn't be an x to the 3rd graph because the extrema has to be bigger than the degree. Let's take a look at letter B and answer the same questions. Is the a value positive or negative? Well, it's a down, down. So I'm going to have to say it's a negative. Is it even or odd? Well, since the end behavior is going the same direction, it must be an even degree. Could it be a 6th degree polynomial? Well, we're going to have to check. How many extrema do we count on this? 1, 2, 3, 4, 5. Could it be a 6th degree polynomial? And that answer is yes. because I counted 5 extrema. And the number of extrema has to be less than the degree of the polynomial. So number 4, state the domain. That's going to be all real numbers. Number 5, state the range. Well, I'm starting at the bottom from negative infinity, and it looks like I top out between 2 and 3. So I'm going to go 2.3. That's just a guess. That's the best I could do based on the graph. Determine the number of relative extrema. We just counted those and we got 5. Determine the number of absolute extrema. Well, I have 1 point that's the highest point of the entire graph. So there is 1. State the intervals where the graph is decreasing. So we're going to have to say decreasing is here, here, and here. So we're going to have to estimate some numbers from, let's say, negative 2.5 until negative 1.5. And over here, let's just say 1.5, or no, 0.5, until over here at maybe 2.1. I'm guessing again. And then 3 to infinity. So for some of those we had to guess because we don't have the exact values or the exact function, but that's the general idea of what is going on there. So let's see now if we can take some information and sketch a graph based on what we know. So we're going to sketch a graph that's degree 4, starts in quadrant 3, ends in quadrant 4. So remember your quadrants go 1, 2, 3, 4. It has a relative maximum at x equals negative 4. Relative maximum. And an absolute maximum at x equals 3. Well, if that's a relative maximum, my absolute maximum has to be higher. Now, if that's my maximum, then my graph can't go any higher than that, so this must be going down. It's a degree 4, so they're both going down. So it starts in quadrant 3, that's here, ends in quadrant 4. And now I'm just going to make stuff up. There we go. That'll work. 1, 2, 3 extrema, absolute maximum, relative maximum. So your graph doesn't have to look just like mine, but that's just a sample. This one's always increasing. So I think that's going to be a cubic. Has a y-intercept at 5. Has an x-intercept at negative 1.7. Always increasing. So this one must be down and then up. So it doesn't have any extrema because it's always increasing. So it never climbs on a mountain. All right, let's take it the next one. This one's an odd degree. It has a relative maximum at y equals 4. It increases to, let's take a look. It increases to x equals negative 3. It decreases to x equals 3. And then it increases. And it has a relative maximum at 4. Let's see. It increases to x equals negative 3. And then it decreases to x equals 3. And then it increases again. Well, I'm thinking something like that. But if it increases to x equals negative 3, And then it has a relative maximum at y equals 4. Oh, it could be 1, 2, 3, 1, 2, 3, 4. Could be there. Increases to this, decreases here, and then goes back up. There we go. Looks something like that. So sometimes you have to kind of contemplate the information you're given. So this one says as x goes to infinity, f of x goes to infinity. And then as x goes to negative infinity, f of x goes to infinity. So based on the end behavior, I think this is a positive even. It has 4 x-intercepts. And then it has a relative maximum at y equals 3. So 4 x-intercepts. So I'm just going to make 4 random intercepts. It's going up and up on both ends. Has a relative maximum at y equals 3. So that means somewhere in here it hits 3. Something like that. So not perfection, but just getting an idea of the shape of the graph. Now in the next two, they give us a graph and they give us some equations, and we're supposed to pick which ones could possibly be correct. So notice the end behavior of this one is down, so that must be even, and a negative leading term. Let's count the number of extrema. 1, 2, 3, 4, ooh, something's going on there, 5. I have 5 extrema. So this must be at least x to the 6th power. Because remember, my power has to be bigger than my extrema. So let's look at this first equation. I'm having a difficult time reading the values here. I believe this says negative 3x to the... Okay, this does say negative 3x to the 5th. And since I've already determined it has to be at least an x to the 6th, it can't be odd. So that one is not correct. So let's take a look here. I've got 1, 2, 3. Oh, that's squared, so that counts twice. 1, 2, 3, 4, 5, 6. So if I multiplied everything together, I would have a negative x to the 6th. So this is a contender. Something to notice right here. I've got x minus 2.5. That means x equals 2.5 is a root. It's a double root because of that squared. And that's what's happening right there. It's a double root. So I think this is a good possibility. Take a look at the last one. I believe that's negative 3x to the 4th. And since I have 5 extrema, I cannot have an x to the 4th. So the second equation is my winner. Now let's take a look at the second one. Notice the end behavior. It's down and then up. So I know this is odd. And it's also positive. So that's going to help me in looking at my terms. How many extrema do I have? I have 1, 2. 2 extrema. So this is at least an x to the 3rd. So let's start with the first equation and count our x's. 1, 2, 3. It's a positive x to the 3rd. So this could definitely be a possibility. Let's take a look at the next one. Count your x's. If I multiply these together, it would be x times x times x. I would have negative 2 x to the 3rd. Well, we just identified this as a positive based on its end behavior. So it is not this one because of the negative. And let's count these. X times x times x times x would give me 2x to the 4th. And it is not even. Based on its end behavior, it had to be odd. So the first equation is the one that best fits this graph.